In the last video, we discussed exponential functions, and in this video, for section 9.2, we're going to discuss the inverse of the exponential function, which is the logarithm. So, the logarithm, like I said, is the inverse. And again, if you remember, inverse means opposite function, how you kind of get back from where you started. So, the inverse of the exponential function that produces the exponent of the exponential function. So if you remember, exponential functions always had variables as their exponents, and this is the way to get that variable down to be solved for if it's not just simply x, if it's something more complex, or if we want to find out, given a certain number, what exponent we would have to raise that base to. So again, we're always dealing with bases in this case. If we had an exponential equation such as y equals b to the x, where b is the base of the exponential function, then the logarithmic equation would end up giving us this x value by taking the logarithm of our base of y and giving us our exponent x. So we're taking this logarithm and applying it on both sides to get the logarithm of whatever base we're given of whatever number this equals to find our exponent. So just some practice here. If we want to convert from exponential form to logarithmic form, we would say, okay, this is going to be our base is 2, so we're going to have a log base 2 of what it's equal to, 8. And we say, okay, well, 2 raised to what power would be 8? Well, that would be 3, so that is our exponent. That gives us our exponent. So the log base 2 of 8, again, what power would you have to raise 2 to get 8 would be 3. I'm going to skip down here to example C. In this case, we have a log base 3, our base is 3, of a fraction here, 1/27. So you say, okay, what exponent would you have to raise 3 to get 1/27? Well, we know it would have to be a negative exponent because it's a fraction, and 3 cubed would give us 27. So in this case, this equals our -3, our exponent. I'm going to skip over here to E, the logarithmic form. This is a lot more generic, as you see. This would be log base t, because that's our base, of x is equal to n, our exponent. So I want you to pause the video here for a second and complete parts B and D. So you should have found that for B, you have a log base 5 of 25 is equal to 2. And for D, you should have had a log base 36 of 6 is 1/2. So we can have fractional exponents again. Those would be our radicals. Likewise, we can convert from logarithmic form to exponential form. In this case, we take whatever our base is, here 7. We raise it to our exponent 2, and in this case, it ends up being 49. Which makes sense. 7 squared is 49. Again, I'm going to skip down to the last one here. In this case, we've got a base of m. We're going to raise it to the nth power, and that is going to produce p. So we didn't have any numbers in this case. This was just a generic form. Again, I want you to pause the video at this point, see if you can fill in B, C, and D, and then resume the video to see if you've done this correctly. So for these three, you should have gotten 4 cubed is equal to 64. 10 to the -2 is 0.01, and again, you can have a negative exponent. That's going to either create a decimal or a fraction. And 27 to the 1/3 power, well, that would be a cube root of 27 is 3. So now that we've done some practice with that, we want to go through and plot some points Notice how I've adjusted the scale here, or the graph here, the axes here, so that our graph will fit appropriately. One thing to keep in mind with a logarithmic function, and I'll write this up here, is that in this case your base is restricted to being positive, because we can't plug negative numbers in, because a negative number would oscillate back and forth depending on if the exponent was even or odd. So we only deal with bases that are positive, and typically we don't worry about the base of 1, because 1 to any power is just 1, so it doesn't really create much of anything other than a straight line. So if we scroll back down here to our first graph, we want to plot some points, and so we want to plug in our values for x. Now since our base is 2, the best thing to do as far as finding numbers that are easy to plot are to put in powers of 2, not multiples of 2, but powers of 2. So technically 1 is anything to the 0 power, so that would be 2 to the 0 power. I'm going to put in 2, 4, 8, and 16. So again, if we think about this, we want log base 2 of 1. So what would you raise 2 to get 1? You would raise it to the 0 power. Likewise, if you continue down, log base 2 of 2, well, you'd raise 2 to the first power to get 2. Continuing, log base 2 of 4, well, you would square 2 to get 4, so that gives you an exponent of 2. Again, we're only talking about the exponents here. Log base 2 of 8, well, in that case you would cube it. And log base 2 of 16 is going to end up being 4, because 2 to the 4th power is 16. Now, we're going to have to readjust our scale if we want to make sure to fit all of these on here. So if we look at our scale here on our x values, we've got 1, 2, 3, 4, 5, 6, 7, 8. So we could just do the first 4, or we can make these increments of 2 so that we can fit everything on. We'll keep this as an increment of 1 and negative 1. Notice I didn't put any, give any y values that were negative. I'll do one of those in a second. So if we plot the points that we have so far, we've got x is 1, y is 0, so we're crossing the axis there. At 2, we are at a value of 1. At 4, we are at a value of 2. At 8, so 2, 4, 6, 8, we are at a value of 3. And at 16, so this would be 10, 12, 14, 16, we are at a value of 4. So it's kind of slowly growing to look something like that. Now, like I said, we didn't get any negative values out. We said we couldn't use a base that was a negative value, but we can get y values out that are going to be negative. So how we're going to do that is by putting in fractions. So for instance, if we put in 1/2 or 1/4, log base 2 of 1/2. Well, what would you have to raise 2 to what exponent would give you a 1/2? Well, if you fill that in with a negative 1, 2 to the negative 1, flip that over, you end up with 1/2. So this would give us an output of negative 1. Similarly, if we wanted to get 1/4, this would be an exponent of negative 2, because we would square the 2 to get 4, and then flip it over to get 1/4. So if we wanted to plot those few points, if we plug in 1/2, which is very small here, we get negative 1. And if we plug in 1/4, which is even smaller, we get negative 2. So you should see that it's kind of approaching the y-axis here, but it's never going to cross, because again, we can never get a negative, we can never plug a negative value in here, because there's no number you could raise 2 to as an exponent that would give you a negative number output. So this is the graph for log base 2 of x. If you compare it to the 2 to the x graph that we did earlier, it's essentially a diagonal flip. If you kind of flip across the line y equals x and flip it over, you would get the graph for y equals 2 to the x. So let's look at a few more graphs. If now we want to look at graphing log of base 1/2 of x, Again, we want to find powers of 1/2, which are going to be similar to powers of 2. So we can use the same values that we used before. Let's use 1/4, 1/2, 1, 2, and 4 this time. If you think about this, log base 1/2 of 1/4. What would you have to raise 1/2 to get 1/4? Well, you would have to square it. Likewise, if you did log base 1/2 of 1/2, well, you would only have to raise it to the first power to get the number back itself. Log base 1/2 of 1, well, what would you have to raise 1/2 to get 1? And be careful here, you're not multiplying, you're raising to powers. So 1/2 to what power is going to give you 1? Well, anything to the 0 power is going to give you 1. Continuing, log base 1/2 of 2. This one's a little bit trickier. Again, think of if you've got 1/2, you want to raise it to what exponent to give yourself 2? Well, you would want to flip it over, so you would want to raise it to the -1 power. Similarly, if you wanted log base 1/2 of 4, then you would have to not only flip this over, but square this, so you would end up with -2. So if we come over here, I'm just going to keep our units as 1 and -1. If we plot our points now, at 1/4, which would be about here, I am up at 2. At 1/2, I am at 1. At 1, I am at 0. At 2, I am down at -1. And at 4, so 3, 4, I am down at -2. So if we connect these dots into a smooth curve, we end up seeing something that looks like this. Now, if you take a second and flip back to the previous graph, you should see that these are mirror images across the x-axis. And that has to do with the fact that this first graph was log base 2, so it was increasing, and log base 1/2 would be decreasing. But they are very similar graphs. So we'll zoom back in here, do a few more examples, and these actually involve solving for x. So, given that you have a log base 4 of what number is going to give you 3. So essentially, if we rewrite this in exponential form, this would be 4 cubed equals x. Well, 4 cubed equals 64. So we can find that value. That's what x equals in this case. Looking at something a little bit different, log base 6 of 36 equals x. Again, sometimes it's easier to rewrite this in exponential notation to say 6 to the x is equal to 36. Well, what exponent would you need to get 36? You would need x to be 2. So x would be 2 in this case. So when x is our value over here, it's talking about our exponent. When it's over here, it's talking about our end value, that once we've raised our base to the exponent. So I want you to pause the video here and try example 17. So you should have found that 25 to the x equals 5. And so if you say, okay, what do I have to raise 25 to? I have to take the square root of 25. Square root is the exponent 1/2. So x is 1/2 in this case. We've got one more example here, and this time we want to actually find the base. So we want to know x raised to the 3/2 power is equal to 64. So in this case, we can go through and solve like we typically do. To get rid of a 3/2 exponent, we would raise both sides to the 2/3. And we would say x is equal to, well, 64 to the 2/3 means we are taking the cube root of 64 and then squaring it. Well, the cube root of 64 is 4. And then we need to square it, so we end up with 16. So our base in this case is 16. Log base 16 of 64 would end up being 3/2. Again, we have a fractional exponent of 3/2. Go back and look at some of these examples. I know this is probably a new concept for a lot of people, so So go back and rewatch this video if you're still confused by anything, and once you feel that you are comfortable with this material, go online, complete your homework for this section.